Okay, we're going to start Geometry, Chapter 1, Prentice Hall. Patterns and Inductive Reasoning. Chapter 1, Section 1. Patterns and Inductive Reasoning. Inductive reasoning is reasoning that is based on patterns you observe. I'm going to write that down here. It's reasoning based on patterns you observe. So let's take a look at some here. Let me pull in a photo. Let's see if I can shrink this down in here. Well, I can expand it actually and just move it to where I want it. So sometimes I'll include photos from the book, just because sometimes it's a little easier to see what they've done instead of having for me to draw it all out. So we have find a pattern for each sequence. Use the pattern to show the next two terms in the sequence. So here we have 3, get the right tool here, 3, 6, 12, 24. We got to see what kind of pattern we can see going on. What am I doing to the number 3 to get to 26? Well, I could say I'm multiplying it by 2, or I'm adding 3. So I could say 3 plus 3, or I could say 3 times 2. Let's see which of these two things work from 6 to 12. So if I were to say 6 add 3, that would give me 9. Well, that doesn't give me 12, which I know I need to go from 6 to 12. So let's try 6 times 2. Well, that would give me, erase that. And go back to pen, That would give me 12. So it seems like times 2 is working. That was 6, I don't know why that got erased. So if I say times 2 here, 12 times 2 is 24, so that does work. So we can say that each term right here, is what they're saying, each term is twice the preceding term. The next two terms then would be 24 times 2 to give you 48, and then you need to use that term, 48 times 2, to get the next term, which would be 96. Here we have a circle that has 1 diameter drawn. The next image is a circle with 2 diameters drawn, equally spaced. The next one, it doesn't look like it just added more lines in here or here. I do have 3 diameters. They're equally spaced, but they're not just adding on to the previous one. So the next circle should have 4 diameters drawn in there. They all need to be equally spaced, so I could go back to this one and add in 2 more, because I already added 1 in here. So I'd have to 1, 2 diameters, 3, 4 diameters. The next one gets a little tricky because I need to be able to add in a 5th diameter. So there's 1 diameter, 2 diameters, 3 diameters, 4, and then the next one would be my 5 diameters, and it gets tricky to draw that in there, but we can handle that. 1, 2, 3, 4, 5. 5 diameters. And here's down here one that you can try on your own should you need a little bit more practice. The answers to these, the problems that follow an example in your book, are at the end of your book in the quick answer section. I'll show that to you in class. So let's move on then to the next example. Before we do the next example, we have something called, another vocabulary term called a conjecture. Conjecture. There's lots of vocabulary in geometry. A conjecture is simply a conclusion that you reach using inductive reasoning. So using observations and patterns that you've taken a look at here. I'm going to write that one down. Is a conclusion you reach using inductive reasoning. So let's take a look at this. It says, make a conjecture about the sum of the first 30 odd numbers. So make a conjecture about the sum of the first 30 odd numbers. You will notice that I like to use abbreviations and shorthand as much as possible. So numbers, if you need that written out. I will do that quite often. You will get used to it and probably like it also. So if I take a look at like the first one, well, the first odd number is just 1. I'm not really adding it to anything, so I would just say that that is just 1. Yay. The next sum of the odd numbers would be 1 plus 2. Sorry, not 2. That's not odd. I need to say plus 3. That's odd. That would be 4. Then I can say 1 plus 3 plus 5. Well, that would be 9. It's really just the previous one and add the next odd number. 1 plus 3 plus 5 plus 7. So really it's just, that's the 9 from the previous term, plus 7 more, which would give you 16. And I could keep going if I really wanted to. So I've got 1 plus 3 plus 5 plus 7 plus 9, which again would be, there's your 16. There's no use in reinventing the wheel. Add 9 would give you 25. You may have noticed there's something special about each one of these numbers here. See if you can come up with it in the time that I'm wasting pointing those out. They are each perfect squares, in case you haven't already. So I could say that this is 1 squared, or 2 squared, or 3 squared, or 4 squared, or 5 squared. And I could keep going. So using this inductive reasoning, I have a pattern here that I've developed. This first term squared, second term squared, third term squared, fourth term squared, fifth term squared. Pardon me. Using inductive reasoning, you can conclude then that the sum of the first 30 odd numbers would be 30 squared, or 900. If you really wanted to sit there and add it all up, you could by saying 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 and so on. But I don't think any of you want to sit there and add up 30 numbers, so we come up with patterns so we can use them. So another try this one could be make a conjecture about the sum. So I'm going to do a try this. TT, try this. Of make a conjecture about the sum of the first 35 odd numbers. And again, that answer would be in the back of the book, should you want to try that one. You can pause this video to try it. I'm going to keep moving though. So the next vocabulary word we run into is something called a counterexample. This is a pretty important idea here that we will use throughout the year. Counterexample. Counterexample. A counterexample is being able to prove that something is false with just one example. One thing can make a whole statement false. You can give me all the examples in the world that make it true. One that makes it false makes the whole statement false. So not all conjectures turn out to be true. You can use one example to, say, disprove a statement or conjecture. So let's try this. We'll try it in example 3. When points on a circle are joined by as many segments as possible, non-overlapping regions are formed inside the circle, as I will show you here. So let's see. We have a circle. Not perfect at drawing circles, but that's okay because you're taking notes and doing the same thing that I'm doing. I'll put 2 points on here and I'll connect them and I'll label them I'll label the regions 1 and 2. So there's 2 points on the circle joined by a line. What if I have another circle? 3 points somewhere on the circle joined by as many lines as I can. And now I have 1, 2, 3, 4 regions. I can keep going with this pattern of adding more dots to the circle. I'm going to have to make my circles bigger so you can see what I'm drawing. 1, 2, 3, 4 dots. Can create as many. So if I'll start with this dot. If I create as many lines as I can from there to each of the other dots. And then from this one, making sure I'm not overlapping many of them. And then I can also go from here. So now I have a whole lot of regions. I'm going to change colors so you can see where I'm writing a little bit better. So I have 1, 2, 3, 4, 5, 6, 7, 8 regions now. So I'll go back to red. Do another circle. I'm going to do a little bit bigger simply for the sake of being able to see what I'm drawing, not because it's proving or disproving any points. I need 5 points now. 1, 2, 3, 4, 5. It doesn't really matter if they're equidistant or not. Starting from here, 1, a line there, a line that way, and a line that way. So this point has got all the lines connected to it. Move on to the next one. The first one is already done that way, so I'll go here, and here, and here. And the same thing from here. The first 2 have been done. Now I need to go to that one and that one. And then my last one is here. So now I need to number all of these regions and see how many there are. I'll start on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Holy cow. Let's put this in a chart form so we can actually see something about this. So let's say we have points on the circle, and then you have regions. So the first circle, we had 2 points and 2 regions. Then the second circle, we had 3 points, but we had 4 regions. On the third circle, we had 4 points, and we had 8 regions. The fourth circle, we had 5 points, and we had 16 regions. Okay, so this table shows that the number of regions for 2, 3, 4, and 5 points. You might conjecture that the number of regions doubles at each stage. So from here to here, oh wait, that doesn't work. Oh, so from here to here doubles, doubles, doubles. So far, every example we've done, that's true. The number of regions, as I continue to increase the point by 1, so this is adding, sorry, let me erase that. Erase and erase. We're going to say this is times 2, times 2, times 2. But on this side, I've only added 1. I'm adding, not multiplying. Okay. But if we make a diagram with a circle with 6 points, we want to see if this conjecture of the number of regions doubles each time. We want to see if that's true, but we need to find a counterexample. Okay, so let's draw a large circle of with 6 points on it. 1, 2, 3, 4, 5, 6. And we'll do our best to connect these nice and neatly so we can see the regions really well. 1, 2, 3, 4, 5. 1, 2, 3, 4. Just getting a little messy there. I'm going to make that a big dot. 1, 2, 3. 1, 2, and then the final one here. And numbering them is the tricky part to make sure we actually hit them all. So I'm going to try and go off in sections here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh, 20 is inside there. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Let's see if I missed any. I've got 30 there. Okay? So I came up with this counterexample that just has 30 regions. And there were 6 points. So that is not times 2, is it? It doesn't work. So here is my counterexample. It doesn't fit the pattern. All you need is one counterexample to disprove your conjecture of saying you need to double the number of regions for each point added. You have a try this if you so choose. Some products have 5 as a factor as shown. I'll set up a chart in here for you. 5 times 7 is 35. 5 times 3 is 15. 5 times 11 is 55. 5 times 13 is 65. 5 times 9 is 45. 5 times 25 is 125. So some products have a factor, some products have 5 as a factor, as shown here. Make 2 conjectures based on these products. Just these here. One that you believe is true, and one that you know is false. Come up with a counterexample to prove or disprove. Answers will be found in the back of the book in your check for understanding. Right? Is that what it is? Yeah. In that section at the back. We're going to keep going though. So, for example, 4. Last example. A skateboard shop finds that over a period of 5 consecutive months, sales of small-wheeled skateboards decrease. So if you were to look on page 6 of your book, there's a little graph that looks something like, let me add something in here. I'm going to put a background on here to say it looks something like this. Along here. And we have January, February, March, April, May, June, and it just keeps going. And then we have, this is a broken line graph there, just where they're not going to start at 0 and count all the way up to This first one being 40, and then 45, 50, 55, 60. I could keep going. We have a point in January right about here, February at 55, March just above 50, April is close to 50, May was right at 45. So, a skateboard shop finds that over a period of 5 consecutive months, sales of small-wheeled skateboards decreased. Use inductive reasoning. Make a conjecture about the number of small-wheeled skateboards the shop will sell in June. The graph shows that, so we can see on the graph then it's kind of trending downward. So if you were to guess, based on what you see, what you observe, the patterns, it looks like you're decreasing in sales about 3 maybe skateboards down here. You lost about another 3 or 4 to get here, another 2. So it looks like on average, I'd say about you're losing 3 skateboard sales per month. So if that's our conjecture, would be that the number of skateboards sold each month decreases by 3, about 3. Therefore is one of my favorite little things. 3 little dots in a triangle means therefore. Therefore, the shop will likely sell 42 skateboards in June. Not super difficult, not earth-shattering. That would be it. Thanks for joining me for the first section.